will be uploading the recorded lectures to Cal, so you can access all the recorded lectures. And by now I have already uploaded you the module descriptor, so you can just have a look what we are going to learn, right? So as you know, in stochastic processes we have so many calculations and some of the concepts are not very easy, so you need to take more time to understand those concepts. So because of that, I thought of uploading short recordings, right? Short recordings means when you take the length of the recordings, it's like around 30 to 40 minutes. So that is, you can take the 2 hours time slot, and then you can just slowly go through the recording and understand the concept. So one thing is, I'm not pretty sure like the last semester whether we will get a chance again to go through all the sessions physically. So because of that, I want you all to go through with all these recordings and just understand the concepts and the sums that I have discussed. And if you have any question, so you can just let me know, right? So we will discuss some of the questions as well, then you will get a good understanding about the concepts, right? Okay, so today I'm going to talk about the first topic in the stochastic processes 2, that is the generating functions, right? So I think before you're coming to this module, you have learned about probability generating functions, right? So what we are going to do in this course is we are going to recap the things that you have learned. So if you have forgotten what you have learned about the probability generating function, you don't have to worry, because I'll be just reminding all the stuff. And especially here we look at probability generating functions for discrete random variables, and some of the useful tools when you're dealing with the probability generating functions, and how you can apply the probability generating functions into stochastic processes. So by the end of this chapter, you will be able to find the sum of geometric, binomial and exponential series, and you know what is a probability generating function, you know how to calculate the mean, variance and the probabilities, and you know how to calculate the probability generating function of geometric, binomial and Poisson distributions, and also how to calculate the probability generating function for a randomly stopped sum, and how to calculate the probability generating function for first reaching times in random walk, and also how to use the probability generating function to determine whether a process will reach for a given state. So those things we are going to discuss under probability generating function. So before we start the definition of the probability generating function, there are some small common things that you have to keep in your mind when you are dealing with probability generating functions. So the first thing is, you should know some of the common sums. That is, when you are doing the sums here, when you are doing the questions related to this probability generating functions, there are some cases where you have to apply the common sums, right? So in that case, those common sums will not be there in your final exam paper, so you have to know what are those common sums, right? So you can see in the screen, the first one is the geometric series. So we know if you have 1 plus r squared plus r to power 3, likewise if you are interested to take the summation of r to power x, where x goes from 0 to infinity, we know the summation of this series we can give the summation of this series by 1 over 1 minus r. But this, what you have to remember is, in this case, r is, when you take the absolute value of the r, it should be less than 1. Right? So using this, actually we can take, if you take a random variable, if x is a random variable where you have the geometric distribution with probability p, in that case you can take, when you take the summation of all the probabilities, where starting from x equals 0 to infinity, it should be equal to 1. So we know when you take any random variable, when you take the summation of all the probabilities, it should definitely add up to 1. But actually using this common summation of the geometric series, you can again prove that. So you can see, when you take probability where x equal to simple x, that is, you have right, x number of failures. So you, in this geometric distribution, they have given the probability of a success is p. So that is, you have x number of failures. So the probability of failure is 1 minus p. So you have 1 minus p to power x into p. So we have to take the summation where x goes from 0 to infinity. So we are taking the summation in both sides. And then you can see, when you take the summation of the both sides, you can take p out from the equation. Right, you can take p out from the equation. Then you have summation x goes from 0 to infinity 1 minus p to power x. So in that case, we have 1 minus p. It's definitely less than 1. So we can apply the common summation. Right, so that is 1 over 1 minus r. In this case, r is like 1 minus p. So you can replace r by 1 minus p. And then finally you get p over 1 minus 1 minus p. So when you just simplify that, you will get this is equal to 1. So we can see the summation, when x is having a geometric distribution with the probability of a success p, summation of x goes from 0 to infinity of the probabilities, the summation of the all possible probabilities is equal to 1. So same thing we can explain, or we can just take the binomial distribution and the exponential distribution, and then we can see the same characteristic. That is, if you take the binomial distribution, right? So in that case, if you just write down the binomial distribution, right? We know if you take p plus q to power n, right? We can just elaborate that as summation where x goes from 0 to n, ncx, p to power x, q to power n minus x, where x is having a binomial distribution with n trials and p is the probability of success. So in this case, if you are interested on taking the summation of these probabilities where x goes from 0 to n, right? So we can just write ncx, p to power x, 1 minus p to power n minus x, where x goes from 0 to n, right? So in that case, right, we can see this whole thing we can equal to, in this case you can see when it comes to 1 minus p, it's like it's acting like q here now, right? So you can just replace this whole term as p plus q to power n. So here your p is same as p and your q is now 1 minus p. So you can put 1 minus p to power n. So p will cancel out, then you have 1 to power n, which is finally simplified for 1. So that is when you take all possible probabilities of the binomial distribution also, that is adding up to 1. So same thing we can show in the exponential power series as well. So what you have to remember is, if you have lambda to power x divided by factorial x, and if you take the summation of 0 where x goes from 0 to infinity, in that case we can see this is equal to e to power lambda, right? In this case we can see this is equal to e to power lambda. So let's see what will happen to the probabilities, how we are going to show that all the summation of all the possible probabilities are adding up to 1 when x is having a Poisson distribution with parameter lambda. So we have the probability where x goes, we are interested about the probability where x equal to simple x, where x goes from 0 to infinity. And this part, this probability, we can replace from the Poisson distribution formula. So that is e to power minus lambda, lambda to power x divided by factorial x. And where x goes from 0 to infinity. Now you can see when you take this summation, you don't have summation for lambda. So you can take e to power minus lambda out. So you have summation x goes from 0 to infinity, lambda to power x divided by factorial x. So this part, now you can replace by this common summation, that is e to power lambda. So you have e to power minus lambda into e to power lambda, that is equal to 1. Right? So there's another useful thing that you can remember, that is when you take e to power lambda, this is equal to 1 plus lambda over n, the whole thing to power n, where n goes to infinity. Right? So if you have this limit, you can replace that by e to power lambda when you are doing the calculations. So you can see when you take the geometric distribution, when you take the Poisson distribution, and when you take the binomial distribution, in all these cases when you take the summation of all the probabilities, they are adding up to 1. Right. So with these things in mind, we can move to the probability generating functions. Right? The probability generating functions. Now the thing is, why we are learning about probability generating functions. Right? Okay, so when it comes to probability generating functions, it's a useful tool to dealing with this discrete random variable, especially when you have when you are interested about the distribution of the summation of 2 or more random variables where they are independent. You can use this probability generating function in order to find out the distribution of these random variables, right? And also this is very important when it comes to stochastic processes, because in most of the stochastic processes we are interested about the summation of random variables, right? So if you can remember, we have discussed about the summation of when it comes to the gambler's ruin. So there you have a repeated process. So it's in cases like that, we are always interested about the summation of 2 or more random variables, right? So you can easily apply this probability generating functions in order to find out the distributions and in order to find out the variances, mean values, right? It would be much easier when you apply the probability generating functions rather than you apply the normal procedure, right, to find out, to do the calculations. Okay, so let's see. Now you can see the probability generating function, the definition of the probability generating function. So if you have a random variable x, the probability generating function of the random variable x is denoted as gxs, right? this is equal to expected value of s to power x, and this is equal to s to power x, right? Because now here you can see the probability generating function is equal to expected value of s to power x. So when you take the expected value of this function, you have to take the function value and multiply that with the respective probability of the x value. So that is s to power x multiplied by the probability x equal to simple x. So you have to take the summation from 0 to infinity, right? So this is the definition of the probability generating function. So with this we can see actually some of nice characteristics, so some of very nice properties in probability generating function. Now let's see what will happen if you apply s as 0, right? Or in other words, what is the value of gx0? So when s value is equal to 0, if you look at this one, so that is s to power, so s is 0. So 0 to power, you have 0 into probability x equals 0. And then you have 0 to power 1 into probability x equals 1. Then you have 0 to power 2, probability x equals 2. Right? So since you have, when it comes to 0 to power 1, we know it's equal to 1. So that is 1 into probability x equals 0. So when you look at all the other terms, since you have the exponents of 0, so that these terms will cancel out. So we are left with probability x equal to 0. So that is, we have gx0 is equal to probability x equal to 0, right? So we have, that is one of the nice properties of probability generating functions. Okay, the next property is what will happen when you substitute or when you replace s by 1. Right? When you replace s by 1. So just we'll have a look. So this is our formula. If you replace s by 1, that is you have s is 1 now. So in this case 1 to power 0 probability x equal to 0 plus 1 to power 1 probability x equal to 1 plus 1 to power 2 probability x equal to 2. So since we have 1 in every term, when you take the x, when you have 1, whatever the exponent is, we know it's equal to 1. So basically you're left with only the probability terms. That is, you have probability of x equal to 0 plus probability x equal to 1 plus probability x equal to 2 likewise. So in other words, you are taking the summation of all the possible probabilities of that random variable. So we know when you take all the possible, the summation of all the possible probabilities, that should add up to 1. So that's why when you take gx1, that should be equal to 1 because it's the summation of all the possible probabilities. Probability where x equal to simple x, where x goes from 0 to infinity. So because of this, we have gx1 is equal to 1. Right? So let's have a look on the binomial distribution. So if x is having the binomial distribution with n trials and p probability to success, so let's see what is the probability generating function of a random variable which is having the binomial distribution. So we can write it as ncx, p to power x, q to power n minus x. This is the binomial distribution. So now when it comes to the probability generating function, so you have to take s to power x and multiply with the probability that is coming from the distribution function, right? So when you look at this one, so for x So for S you have the exponent as x, and for P you have the exponent as x. So I can just combine these two terms and write NCX P is to power x and Q to power n minus x. Right? So that is PS plus Q. Now when you look at this one, actually this is like a binomial distribution, right? Where you have this your P value, the probability of success as PS, and where the Q value is equal to Q. So when you have this term, this is a common summation of the binomial distribution. So you can replace that by P plus Q to power n. So in our case, P is PS, Q is Q. So the whole thing to power n. So that is, when it comes to the binomial distribution, the probability generating function we can write as PS plus Q to power n. So actually you can just check the values of the probability generating function, right? So when it comes to when S equal to 0, we can substitute 0 here, that is P into 0 plus Q to power n. So P, this term will become 0, so you have Q to power n. So Q to power n means all the trials are failures, that you have 0 successes. So in other words, you have the probability where x equal to 0, right? And we can check what will happen when S equal to 1. So we can just substitute 1 here, that is P into 1 plus Q to power n. So that is P plus Q to power n. So we know in binomial distribution P plus Q is equal to 1. So that is 1 to power n. Finally we have that as 1. Right, so what you can do is, now you can see the characteristics. So the properties of the probability generating function is satisfied when it comes to the probability generating function of the binomial distribution. So you can just take some of the values for S and some of the and then check the respective values of the probability generating function, and just you can plot, right? You can take any number of trials and the probability of success and see the shape of the distribution. So in this case you can see here the x is having, here this random variable is having a binomial distribution with 4 trials, and the probability of a success is 0.2. So in that case, when you just calculate the values of the generating function, so you will get different values, and if you plot you will see this kind of a shape. Right, so let's check this with the Poisson distribution as well. So let's say x is having a Poisson distribution with parameter lambda. So we know when it comes to the probability where x equal to simple x, what do we have to do? We have to take lambda to power x, e to power minus lambda divided by factorial x. So now we are interested in calculating the probability generating function. So what you have to do is that when it comes to probability generating function, so you have to take s to power x multiplied by the probability. So the probability is coming from this distribution function. So we can replace that as lambda to power x, e to power minus lambda divided by factorial x, where x goes from 0 to infinity. And now you have e to power minus lambda. You can take out because it has no relationship with x. So here in your numerator you have lambda to power x and s to power x. So you can combine and write it as lambda s to power x divided by factorial x. Right? So then you have, when it comes to this term, we know this is a common summation, right? when you have lambda to power x divided by factorial x, we can write it as e to power lambda, right? So now our lambda is like lambda s. So you can just take this term as a common summation and you can write it as e to power lambda s. Right, so here you have e to power minus lambda and e to power lambda s. So when you simplify it furthermore, we can write, when you take e to power lambda out, that is e to power lambda s minus 1. So this is the probability generating function of a Poisson distribution. So as in the previous case, you can take any value for the parameter lambda and just check some of the values of the probability generating function and plot it and say. Okay, and then when it comes to the geometric distribution, so let's say x is having a geometric distribution, right? And then we, if the probability of a success is p, when we want to calculate the probability where x is equal to simple x, that is we have x number of failures. So 1 minus p is the probability of a failure to power x into p. Or in other words, we can write it as pq to power x, right, where q is equal to 1 minus p. So in this case, if you are interested in generating the probability generating function, so we have to take s to power x, p into q to power x, right? So we take p out and then write q s to power x, where x goes from 0 to infinity, right? And now this is a common summation, right? So this is the geometric series. So this common summation you can replace by, if this is like r to power x, this is 1 over 1 minus r. So now our r is like qs. So that is 1 over 1 minus qs, but here we have p. So when it comes to the geometric distribution, the probability generating function is p over 1 minus qs, right? So likewise, we can generate the probability generating function for binomial distribution, for the geometric, for the Poisson, right? For any discrete random variable, we can just generate the probability generating function and say. Okay, so now it's very important because in most of the cases we can use the probability generating function in order to calculate the probabilities of the random variables, right? Let's see how can we do that. Now we know when it comes to, if you have a random variable capital X, so the probability generating function is denoted as GXS. So that is the expected value of s to power x, right? So actually this is, we can write this one as the probability, right? So now just for notation, we'll take simple px is the probability where x is equal to simple x. Now when it comes to the probability generating function, what we do is we have to take s to power x and multiply that with the corresponding probability. So with the notation, I'll write it as simple px. So where you have to take the summation from 0 to infinity. So that is when x is equal to 0, right? So that is, you have p0 into s to power 0. So s to power 0 is 1. So you are left with p0. And when x is equal to 1, you have p1 s to power 1. That is p1s. Likewise, you have plus p2 s squared, p3 s to power 3, p4 s to power 4. Likewise, up to infinity. But we know for any probability generating function, we saw that when you replace or when you substitute 0 for s, that is equal to p x equals 0. So that we can see from here as well, because when you substitute 0 for s, that is gx0, and all these terms from the second term onwards, all these terms will cancel out because you have to multiply each term by 0. So you are left with only p0. So in other words, p0 means px equal to 0. Right? So let's see what will happen when you take the first derivative. So this is our function. So when you take the first derivative, p0, that's a constant. So that will be equal to 0. So you have p1, and when you take the first derivative of s, that is 1. Then you have p2 into s squared. So that is p2 into 2 times s plus p3 into 3 times s squared. Right, so that is when you take the first derivative, you can see you have p1 plus 2 times p2s plus 3 times p3 into s to power 2 likewise. So what we can do is now we can substitute 0 for s. So when you substitute 0 from the second term onwards, all these terms will cancel out. You can see. So you are left with P1. So P1 is equal to probability x equal to 1. And that is how we got that is by substituting 0 here. That is G dash x 0. So you can see when you take the probability generating function, when you right away substitute 0, you will get P0. That is the probability where x equal to 0. And when you take the first derivative and substitute 0, you get the probability when x equal to 1, P1. Alright, so likewise if you want to take the P2 value, right, where x equal to 2, you have to take the second derivative. So when you take the second derivative of this, p1 will cancel out. Then you have 2p2 plus 3 into 2 into p3 into s and plus 4 into 3p4 s squared likewise. And then when you substitute 0 here, you have g, the second derivative, g double dash xs is equal to 2p2. So we are interested about p2. So you have to take the second derivative, and when you divide it by 2, you get p2. So if you go for the third derivative using the same method, you can just calculate the third derivative. So you can see a pattern now. See, P0 is equal to the probability generating function. P1 is equal to the first derivative. P2 is equal to second derivative divided by 2. And P3 is equal to third derivative divided by factorial 3. Right? So in other words, I can say P0 is probability generating function divided by factorial 0. And P1 is first derivative divided by factorial 1. P2 is second derivative divided by factorial 2. P3 is third derivative divided by factorial 3. So if you are interested in Pn, you have to take the nth derivative and substitute 0 for s, right, divide by factorial n. Okay, so this is one of most important things where you can apply in your calculations, right? When you want to find the probabilities using the probability generating function, you can apply this, right? So just see this example. So let's say you have a random variable capital X, and it's a discrete random variable, And the probability generating function of the random variable is given by this formula. That is, you have s over 5 into 2 plus 3 into s to power 2. So now we have to find the distribution of x, right? So since x is discrete random variable, finding the distribution means you have to find all the possible values of x, and then you have to find the corresponding probabilities. So we know when you have a probability generating function, if you just take the probability generating function right away and when you substitute 0, you will get the value of P0. In other words, the probability where x is equal to 0. So you can do that. You can take the probability generating function, and when you substitute 0 for s, you can see it's adding up to 0. That is, probability where x equal to 0 is 0. And then we can take the first derivative, right? So when you take the first derivative of the probability generating function, here you have 2 over 5 plus 3 into 3, that is 9 over 5 into s to power 2. So when you substitute 0 for the second derivative, this term, second term will cancel out. Then you get 2 over 5. So from the first derivative, you get the P1 value. That is the probability where x equal to 1. So you can go to the second derivative and see. So this term will cancel out. Here you have 2 into 9, that is 18 over 5 into s. So this is the third derivative. When you again substitute 0, this is 0. That is from the second derivative. So from the second derivative, you can get P2 value, but it's 0. Right? And then you have to go to the third derivative. So that is 18 over 5. Right? So when you substitute 0 for s, you get right? You can just take this one, and then what you can do is you can just substitute 0 here, and then you have 18 over 5. But we know when you take the third derivative, you have to divide it by factorial 3 to take the P3 value, right? So that is 18 over 5 into 1 over factorial 3. So you have 3 over 5. That is P3 value is 3 over 5. So you can see when you just go for a fourth derivative, it's 0 because you have a constant there. So we don't have to bother about the values where we don't have to go for the more derivatives because all of them will be equal to 0. So you can just write it gx to power r s, the generating function. When r is greater than or equal to 4, it's adding up to 0. So the probability will also be equal to 0. So for this discrete random variable, actually you have two possible values. When x equal to 1, probability is 2 over 5. When x equal to 3, probability is 3 over 5. So actually that's right, right? Because here that's correct, right? Because when you see these two probabilities, when you add up these two probabilities, it's adding up to 1. So that is one of the properties of the distribution functions of discrete random variables. So all the possible values of the probabilities should add up to 1. So we can nicely see that property here. Okay. So what you can do is you can like this, you can just identify the distribution of a given random variable by calculating the probabilities using the probability generating function, right? So what happens here is when you take a probability generating function that actually shows the whole sequence of probabilities for a given random variable. We can define all the probabilities of a given random variable using the probability generating function. So actually that is a unique thing. right? When you take a random variable, the respective probabilities of that random variable is unique to that random variable, right? So if you just think it in other way, that is, if the probabilities are unique, if you can find out the probabilities using the probability generating function, that is, the probability generating function is also a unique one. Alright, so using this uniqueness of the probability generating function, sometimes we can identify the distribution of a given random variable. Right? So there is another small thing that you have to remember. Now let's say there are two power series which have been defined on a same interval, but that interval should consist 0. Right, so let's say you have a power series AS, you have another power series BS, right? And these are like you have these are two probability generating functions. AS and BS are probability generating functions. Okay. And if AS and BS are probability generating function, and if this S value is defined at an interval, if this S is defined in this interval minus R dash and R dash, between S is in between minus R dash and plus R dash, then if these two probability generating functions are equal, in other words, all of these probabilities should be equal as well. That is, simple an and simple bn are the probabilities. So if two probability generating functions have been defined in a same interval which consists 0, then those two probabilities should be equal as well. An and Bn should be equal as well, right? So actually we can use this property as well when we are using the probability generating functions. Okay, so there's another thing, another advantage of using the probability generating functions, that is, we can find out the expectation and the moments using the probability generating function. So actually when you take the probability generating function and when you take the first derivative of the probability generating function, just I will have, yeah, here, just have a look on this. Okay, so this is the probability generating function, and this is the first derivative of the probability generating function, right? So when you take the first derivative of the probability generating function, what will happen? Just see what will happen if you substitute 1 for the first derivative there. Right, so in that case, if you substitute 1 for the first derivative, right, so in this case, this is the first derivative, we are going to substitute 1 for the first derivative. That will ultimately give you the expected value of x. Right, that is actually giving the expected value of x. We can nicely prove that as well. So it's like this, when you take the probability generating function, we know that is equal to s to power x into px, where x goes from 0 to infinity. And then in this case, if you take the g dash x value or the first derivative, so you have x into s to power x minus 1 into px, right? So you have to take the summation from 0 to infinity, and we are going to substitute 1 for s, so this term will go out. So we have x goes from 0 to infinity, x into px. So in other words, what do we have to do? We have to take the possible value of x and multiply that with the respective probability, right? So that is, in other words, how we find the expected value of x, right? So that is, if we want to find the expected value of x for a given random variable, we can take the probability generating function and then we can take the first derivative of the probability generating function and then we can substitute 1 for that, then we'll end up with the expected value, right? So let's say what will happen when you take the kth value, right? When you take the kth derivative and when you substitute 1, what will happen? So when you take the probability generating function, right, so this is the first derivative. So when you go to the second derivative, you have x into x minus 1 into s to power x minus 2 px, right? So likewise, when you go to the kth derivative, you have x into x minus 1, x minus 2, likewise x minus k plus 1, s to power x minus k into px, right? And when you substitute 1 for s, this s to power x minus k term will cancel out. Then you have x into x minus 1, x minus 2 up to x minus k plus 1, then px, right? So in other words, what have we done here is we have taken the expected value of all these, we have taken the expected value of this function, right? X into x minus 1, x minus 2 into x minus k plus 1. This is a function of x. So we have taken the function and multiplied that with the probability. So that is the expected value of this function. So when you take the probability generating function and then when you take the kth derivative of that, right? When you take the kth derivative and when you substitute 1, it will give you the expected value of this function, where starting from x to x minus 1, the multiplication of x to x minus 1, x minus 2 up to x minus k plus 1. Right? So let's see, using this, how we are going to find out the expected value and the variance of a Poisson distribution. Okay, so let's say x is having a Poisson distribution with parameter lambda, and we know the probability generating function of the Poisson distributions, that is e to power lambda into s minus 1. So we need to find out the expected value and the variance using the probability generating function. So of course we know when it comes to a Poisson distribution, the variance and the expectation is equal to lambda. But we can just check whether the results we know are applicable by applying to this question. So what I'm going to do is, when you take the first derivative of the probability generating function and then when you substitute 1 to that, you will get the expected value. So you take the probability generating function and take the first derivative. So you can take e to power lambda into s minus 1, but the exponent you have to take the derivative of the exponent, that is again equal to lambda, right? So that is, you have the first derivative lambda into e to power lambda s minus 1. Now we are going to substitute 1 for this. So that is e to power lambda into 1 minus 1. So that is 0. That is lambda into e to power 0. So e to power 0 is 1. So lambda into 1 is lambda. So you can see the expected value of a Poisson distribution. We can say it's equal to lambda. And when it comes to variance, so we know the variance is equal to expected value of x squared minus expected value of x, the whole thing squared. So expected value of x, we know lambda, so we can substitute this as lambda squared. But now we have to find the expected value of x squared. So for that, what I'm going to do is, I'm going to take x into x minus 1, right? So if I'm taking x into x minus 1, this multiplication, the expected value of this multiplication, so from the previous one, see, from this thing I can take when it comes to x into x minus 1 expected value, I can construct using this formula, right? So that is, I'm going to take the second derivative and then going to substitute 1, right? So this is the first derivative. So when you take the second derivative, you get lambda squared into e to power lambda s minus 1. And now we have to substitute 1 here. So you'll get lambda squared, because this term will be equal to 1, e to power 0. It will become e to power 0, that is equal to 1. So this is lambda to power 2. So now when you take the variance, we know expected value of x squared minus expected value of x whole thing squared. So this I can write expected value of x into x minus 1. So here when you simplify, you have expected value of x squared minus expected value of x. So in order to remove this additional term, I'll take plus expected value of x minus expected value of x whole thing squared. So this term's expectation, we know lambda squared, plus expected value of x is lambda minus expected value of x is lambda, and you have to take the square term, that is lambda squared. So lambda squared will cancel out and we are left with lambda. So we can see, when you have the probability generating function, we can easily find out the expected value and variance. Now actually this is a known distribution. So you can apply the same concept when you have an unknown distribution as well. Alright. So let's see what will happen how can we apply the probability generating function for a sum of independent random variables, right? So let's say if you have two random variables x1 and x2, and if you are interested about the expectation of s to power x1 plus x2, if these x1 and x2 are independent, I can write this as expectation of s to power x1 into s to power x2. So this is one of the important properties in probability generating functions, and that is very useful, right? So that is, if you have x1, x2 up to xn independent random variables, let's say y is the summation of these n random variables, and we are interested in the probability generating function of y, right? So in other words, this is equal to, what you have to do is, you have to individually find the probability generating function of each of these x's random variables and take the multiplication that will give you the probability generating function of the random variable y. So that is, you can replace the summation by the product when it comes to probability generating function. Right, so we can easily see the proof here as well. So we are interested in taking the probability generating function of the random variable y. So that is the expected value s to power x plus x2 plus x1 plus x2 plus up to xn. So that we can replace by the summation, you can replace by the product, that is s to power x1, s to power x2 likewise. So since these are independent, I can take the expectation, right, for each and every random variable separately. So that is expected value of s to power x1, expected value of s to power x2, likewise expected value of s to power xn. So when you take this term, this is the probability generating function of random variable x1. This is the probability generating function of random variable x2. This is the probability generating function of random variable xn. Likewise. So what you have to do is, so here we have the product of the probability generating functions of random variables x1 up to xn. So that is, when you take the probability generating function of random variable y, you can take it as the product of these random variables. Right, so as for an example, if you have two random variables x and y, both are having Poisson distributions. X is having a Poisson distribution with parameter lambda and y is having a Poisson distribution with parameter mu. So what you can do is, if you are interested in the probability generating function of x plus y, this is equal to probability generating function of x into probability generating function of y. So since x is having a Poisson distribution, we know the probability generating function of a Poisson distribution is e to power lambda into s minus 1. And here in y variable the parameter is mu, so the probability generating function we know when it comes to Poisson distribution, that is e to power mu s minus 1. So when you further simplify, you have e to power lambda plus mu into s minus 1. So when you look at this is showing the characteristics of a probability generating function of a Poisson distribution, where your parameter is lambda plus mu. Right, so that is, when you take the summation of these two random variables, they are also having the Poisson distribution with lambda plus mu as the parameter. So that is something we know, right? So that it can be seen by using the probability characteristics of the probability generating function. So I think the probability generating functions and how, when you are given with a random variable, how to form the probability generating function and how to calculate the probabilities using the probability generating function, how to calculate the expectations and the variance using the probability generating functions, those things are clear. So we'll stop at this point for this chapter, and we'll see in the next session how can we use these probability generating functions when it comes to the stochastic processes, right? Thank you so much. So if you have any question, you can just inform me. Thank you.